All right. Hello, everyone. It's a pleasure to have Bastien Lapierre from the University of Zurich present his work with Titus, Neupert, and Luka Trifunovic on topological localized insulators.
Great. Thanks, Anton. So, hi, everybody. Thanks for coming to my talk. So, my name is Bastien Lapierre. I'm a PhD student working at the University of Zurich in the group of condensed matter theory led by Titus Neupert, and I'm working under the supervision of Luka Trifunovic. So today I'm going to present some recent preprint that we put in the archive about a month ago that was written with Titus and Luka about a new topological phase of matter that we introduced and named topologically localized insulators, or TLI for short. So these, in a nutshell, these basically correspond to systems that are localized by disorder, such that the bulk is fully localized, but one can still define some notion of topology in that kind of systems. Okay, so as the title suggests, we're going to deal with topological properties of particular types of insulators. It will be insulators that are insulating because of localization, because of disorder. So first, there are different types of insulators, right? So there are different mechanisms to have insulating behavior in the material. So for instance, in crystals that have translation invariants, one can have band insulators where the system is actually insulating because the Fermi level is lying in a band gap. There can also be Mott insulators where the system is actually insulating because of the electron-electron interactions, because of the Coulomb repulsion between the electrons. And there can also be so-called Anderson insulators that are insulating because the wave functions of the Hamiltonian is actually localized in space because of disorder, because of the phenomenon of Anderson localization. So in the case of band insulators, the relation to topology has been studied a lot and goes under the name of topological band theory. So this basically classifies different equivalence classes of band insulators that cannot be smoothly deformed one into another without breaking some conditions. So here, we cannot interpolate between two different topological insulators without closing the bulk gap, without going to a gapless phase in between, okay? And in part, some gapless boundary states that appear that cross the Fermi law, okay? So the way we can classify those different equivalence classes of insulators is by defining some topological invariants. So for instance, in the case of the two-band Chen insulator, the Bloch Hamiltonian defines a map from the 2 torus Brillouin zone to the Bloch sphere. And then the number of times this map is wrapping the Bloch sphere will actually define our topological invariant. And the important physical consequence of having a topologically non-trivial insulator is that if we apply open boundary condition that we have some surface, then there will be some gapless modes that will propagate along this surface, okay? And this is because of this bulk boundary correspondence that relates the topological invariant of the bulk to gapless surface states on boundaries. Okay, so this talk will actually be more about the link between Anderson insulators, insulators that are not conducting current because they are disordered, to topology, okay? So I'll first try to recap some very simple aspects of disorder and localization. So I'll first introduce Anderson localization. So here we consider a non-interacting systems on a lattice, okay? So it can be well described by a tight banding Hamiltonian. So this Hamiltonian will basically have two terms. It will have a kinetic term that will take to be, let's say, nearest neighbor hopping, and it will have an on-site potential. And we'll take this on-site potential to be given by a random potential to modelize this disorder. So we take this WR to lie in the interval minus WW uniformly. And these are just random variables that are taken uniformly in that interval. And W here is called disorder strength. So it turns out that in dimension 1 and 2, in the thermodynamic limit, well, one can write down a scaling theory for the conductance. And this scaling theory tells us that in dimension 1 and 2, in the thermodynamic limit, we would always flow to a zero conductance state, which is insulating. And all the eigenstates in the thermodynamic of the Hamiltonian will actually be localized by the disorder. But then what happens in dimension 3 and higher dimensions also is that we can induce, by increasing the disorder strength, we can actually induce some finite metal to insulator transition. This is because here in this flow diagram for the beta function of the conductance, we have some unstable fixed point. And then in the thermodynamic limit, either we can also flow to an insulator because of this order, or we can actually flow to finite conductance state, which will be metallic state. So we have really a finite metal to insulator transition. So the way to see it, for instance, if we consider one band here in this energy density of state diagram, if we increase this disorder strength, then at the edges of that band, there will be some localized state that will start to appear. And then the boundary between those localized state and the delocalized states in the middle of that band is called mobility edge. In particular, you see that if we increase the disorder strength such that we are higher than this critical value of the disorder strength WC, all the states in the thermodynamic limit get localized, and we're always insulating. So the typical form of the wave functions of the eigenfunctions of the Hamiltonian will typically be this exponentially decaying wave function that are defined on a compact support. And here then we can define some characteristic length, which is called localization length for those wave functions. And this will turn out to be the order parameter of this phase transition and diverges at the phase transition. And the divergence is given by a critical exponent nu here. So that is for Anderson localization. So now I will briefly discuss some different aspects, some different link between disorder and topology. So certainly the most famous of all is the integer quantum Hall effect. So we know that when we apply an external magnetic field in those systems, the whole conductivity will be quantized, and it will have this. It will be quantized on some plateaus. But actually, the precise existence of these plateaus relies on the presence of impurities and localization. So, because the system is very dirty, there will be a lot of impurities that will create some random potential in the system. And this random potential is going to break the translation symmetry that we had. And this will actually broaden the Landau levels. So in the clean case, we'll just have some infinite set of Landau levels at discrete energies. And by increasing the disorder, by putting some impurities, actually those Landau levels are going to broaden, make some kind of bands. And at the edges of such bands, the states will actually be localized, while in the center of those bands, around the energy of the original Landau levels, the states will be extended. They will still be delocalized, such that if you look at the spectrum, if you tune your Fermi energy and you start populating states that correspond to these localized states, because they are localized and there is no tunneling between those localized states, this will not affect the whole conductivity. It will not affect the current. Therefore, the current will only increase by an integer value when we go through these extended states, right? But in the mobility gap, which is defined by the set of all these localized states here, the whole conductivity just stays constant by changing Fermi energy. Okay, so this is for quantum Hall effect. But then the role of disorder has been explored a lot in the context of topological insulators, and in particular in the tenfold way classification of topological insulators. Okay, we know the tenfold way classification just tells us that given the dimensionality of the system, as well as the non-spatial symmetries that this system can have, time reversal, particle Hall symmetry, or Carroll sublattice symmetries, one can or not have topological phases that are defined, okay? In particular, we can obtain this whole classification just by asking that at the boundary of the topological insulator, we can actually evade Anderson localization, meaning that if we apply some boundary disorder, the states will remain delocalized. So this goes under the name of Anderson delocalization. And there, the delocalized boundary states of the TI will survive disorder if the disorder actually respects the symmetries of the system and does not close the Borg gap. Okay, so this is related to the absence of atomic limit for TIs. And this really means that the boundary of topological insulators are anomalous. They cannot be realized as standalone because they cannot be localized by disorder. While we know that usually for systems, for instance, of dimension 1 and 2, as long as we put a tiny bit of disorder, we would expect everything to localize in the thermodynamic limit. So from a mathematical perspective, the fact that we might evade Anderson localization in a topological insulator is actually related to the possibility to add topological terms in the continuous Hamiltonian that describe the low energy physics of such systems. So if you cannot add topological term in such a Hamiltonian, then you would expect to just flow to an insulator in the thermodynamic limit. But actually the beta function would be changed if we add some topological term, and you might on the boundary actually flow on a metallic state instead of an insulating one. And therefore you might evade localization, Anderson localization, because of such topological terms. Okay, the last thing I wanted to mention about the link between disorder and topology is the concept of topological Anderson insulators, or TAI. So these are systems where by increasing the disorder strength, one can induce a transition from a trivial insulator to a topological one. So a naive way to maybe understand it is, for instance, to look at Chern insulator, the two-band Chern insulator. So here we know it's a two-band gap model. And as long as we apply a bit of disorder in such a system, what will happen is that if we look at the energy as a function of density of states, in the thermodynamic limit, almost all the states will be localized. There will be those red ones, but there will exist two delocalized states, let's say E1 and E2, in the bulk that will survive this disorder. And therefore, if we tune the Fermi level here along this energy axis, because the two band carry opposite Chern number, let's say of -1 and +1, then, well, by populating the first delocalized states, actually will jump to a quantized Hall conductivity. But then by also populating the second delocalized state, because they have opposite Chern number, opposite Hall conductivity, we'll go back to 0. So this you could compare to what we've seen just before for the integer quantum Hall effect, but here we have a finite dimensional Hilbert space. So instead of having this staircase kind of shape for the Hall conductivity, here we can only go from 0 to 1 back to 0 by tuning the Fermi level. Okay, but if we increase these orders further in that kind of system, in this Chern insulator, what will turn to happen is that we have this phenomenon of levitation and annihilation. So we have these two delocalized states, E1 and E2, and by increasing this order, what will actually happen is that they will repel each other like this, as you can see. And then if you increase it further, the disorder strength, then they will annihilate each other, and all these pairs of delocalized states carrying opposite Chern number will actually vanish. And then you will be back in a trivial Anderson insulator that has no topological properties. But you see, because of this particle form of this curve, that you could start from a trivial insulator and be driven to a non-trivial Chern insulator by increasing the disorder strength. Okay, so this is a rather naive way of thinking about it. And such phenomena of driving from trivial to topological Anderson insulator has been observed actually in numerics, right, in Mercury telluride quantum wells. By starting from trivial insulator and increasing the disorder strength, one could be driven to this yellow island here that has quantized Hall conductance to its curve H. Okay. This has also been observed beautifully in photonic systems, where starting by from a trivial insulator at 0 disorder, one could be driven by increasing the disorder strength to a topological phase. But here one should note also that such a phase will be connected to the topological band insulator that is defined at 0 disorder right here. Okay, so that's it for these connections between disorder and topology. So now I would like to introduce the main, the concept that we introduced, that is this topologically localized insulators, or TLI. So the main question that we ask here is, can we construct a non-trivial insulator such that all the box states are fully localized? So you would expect that, well, when all box states are localized, everything is trivial. But it turns out that if the box states, but one can actually still have a notion of topology here that I will describe. In particular, we have found such an example in three-dimensional systems in class A, which are disordered. So just note that in class A in 3 dimensions, there is no strong topological insulating phase in the tenfold way. So we don't have translation symmetry because of disorder, and we don't have any of those non-spatial symmetries. So naively, one might be tempted to think that things should be trivial. But it turns out that instead of having only a boring Anderson insulator, one can actually have an infinite equivalent classes of disordered insulators that we call TLI, that are classified by some Bock invariant that takes a Z classification. And there will be some boundary signature here that I would just describe later. In particular, if one tries to interpolate between two of such TLIs that are topologically non-equivalent, then what will happen is that in between, one will need to go through a metallic phase, meaning that here the constraint in both cases is that the Bock is fully localized, but by interpolating between the two, at some point, some states in the Bock will actually start to be delocalized, and therefore those phases will be separated by a metallic phase. So this should be reminiscent of the case of topological band insulators, where when one has two topologically distinct topological insulators, by interpolating smoothly between the two, one would necessarily need to close the Bock gap and get also into a metallic phase. So this is kind of the analogy that one could draw between the two cases. Okay, so to describe a bit more what is this TLI phase, let's discuss what happened on the Bock and on the boundary and compare it to the tenfold way. So in the case of the tenfold way, we have seen, for instance, with the chain insulator just before, that the Bock is not fully localized, right? There is still for instance, in the chain insulator, there were still two delocalized states that were appearing in the Bock, while the boundary is fully metallic. So therefore, the states in the boundary are delocalized. Here in a TLI, we'll shift everything by, let's say, 1 degree of localization. So the Bock will be fully localized, while the boundary will actually not be fully localized. There will be some states on the boundary that cannot be localized by disorder, okay? So in some sense, yeah, we shift everything by 1 degree of localization. And here, one should really think of the boundary of the TLI as being insulating. It's not a metallic boundary, but even though it's insulating boundary, it will still host some delocalized states. In particular, so if we plot, so we really have a 3-dimensional system, but if we plot the spectrum as a function of, let's say, one of the 3 directions, let's say the Z direction, and we apply open boundary condition at both sides here, it will turn out that each surface here will carry some quantized Hall conductivity, let's say of E squared over H and minus E squared over H. So on each surface, this Hall conductivity will be of opposite sign. And there will be exactly 1 delocalized state per boundary, per surface. So 1 delocalized state on that surface, denoted by this red cross, and another on the other surface. But then one should note that as the Bock is fully localized, there will be no possible way for annihilating those 2 delocalized states, because they would need to go through the Bock. But the Bock is fully localized. Therefore, you cannot just bring them together and annihilate them as you could have done for the Bock of a chain insulator. So in that sense, the 2-dimensional boundary of a TLI is really anomalous, cannot be realized as a standalone, because, well, it has some quantized Hall conductivity, okay, that will survive to any disorder strength that is applied on the boundary, okay. And this is really different from disorder 2-dimensional chain insulator, because here we know that when we apply disorder in the bulk of the chain insulator, at some point, there will be this pair annihilation that will happen, and then will be driven to a trivial insulator if the disorder strength is large enough. But here, because this pair annihilation cannot happen because there's only 1 delocalized state per surface, then this will survive any boundary disorder. So in that sense, the boundary is anomalous and can be understood as half a chain insulator. So half in the sense that the boundary will carry only a single delocalized state instead of having 2 of such. Okay, so this is the general idea of this TLI, but then one now needs to come up with a concrete model to build it, whether it is possible or not. So let's try to illustrate one possible way to construct such a phase. So we'll start from chain insulator in 2 dimensions, and then we'll just tag them in, let's say, the Z direction. So we stack these Chern insulators in the Z direction. We put a finite number of such, let's say NZ of such, and then we can represent the energy as a function of Z, right? So the two-band Chern insulator has two bands, right, of opposite Chern number, opposite Hall conductivity. Let's say negative energy states carry minus E square over H Hall conductivity, and positive one will carry plus E square over H Hall conductivity. And then we can define some projector at layer Z on the negative energy states and projector at layer Z on the positive energy states. So if we decide first to not couple the layers, but just consider the layers individually, what we can do is that we can consider all the states here. And because this has Chern number -1 and this has +1, the sum of the two has Chern number 0, and we can just localize all the states by applying disorder. So in that way, we can localize and trivialize each layer. And what we'll end up with in the end would just be a trivial Anderson insulator. So this is maybe not very interesting. Now let's try something else. Instead of not coupling the layers at all, now we'll couple the neighboring layers in the Z direction. So it means that we'll couple, for instance, layer Z with layer Z+1, and in particular, we will project on the subspace of the Hilbert space that is spanned by the negative energy states at layer Z and the positive energy states at layer Z+1, okay? So therefore, in that case, we still have 0 Chern number in total, and we can localize all the states in the bulk by disorder. But what will happen, as you already see, is that if we apply open boundary condition in the Z direction, clearly there will be some delocalized state that will survive here, that will carry a Hall conductivity of E square over H, and on the other boundary, they will carry a Hall conductivity of minus E square over H. So we really have these boundaries that still host one delocalized state each in the case of disorder with this construction. And in particular, so this is the surface signature, but in particular, if we look at the bulk, if we thread in the Z direction, if we apply in the Z direction some magnetic field such that we thread through each layer some magnetic flux by one quantum flux phi 0, then by the Streda formula, we'll get a transfer from one electron from the layer Z at negative energy to layer Z+1 at positive energy. Therefore, we get a net electric polarization that is quantized to 1. So here we get some magnetoelectric effect in the translationally invariant bulk, while we get a Hall conductivity of opposite signs on the surfaces of the system. Okay, so that's the global idea to construct this model. So in particular, now we can construct the Hamiltonian a bit more precisely. So we first define, this vector GR alpha, which is just a linear superposition of layer Z and layer Z+1, of layer Z and layer Z+1, basically. Here alpha, here just some sublattice degree of freedom that takes value 1 or 2 because we deal with the two-band Chern insulator. Okay, so then we just take this linear combination of layer Z and Z+1, and we construct some disordered Hamiltonian from here in this basis, okay? So now what we just want to do is that we want to project this on the subspace of the Hilbert space that is spanned by negative energy states at layer Z and positive energy states at layer Z+1. So we just use our projectors to have the Hamiltonian between the layer Z and Z+1 to just be this disordered Hamiltonian projected on this particular combination of states. And then the total Hamiltonian is just obtained by summing all the Hamiltonian at each layer and summing over the layers, okay? So then if we apply periodic boundary conditions, we can actually show that these functions WR alpha, that are just these two projectors acting on the linear combination of layer Z and Z+1, such states WR alpha are actually exponentially localized in space, okay? And they form an orthonormal basis. Therefore, it means that with periodic boundary conditions, the unitary U that diagonalizes the Hamiltonian has exponentially decaying matrix elements. And in that sense, although the Hamiltonian has no translation invariance because of this disorder, because it has disorder, the unitary U that diagonalizes it still has translation invariance. But this is very fine-tuned. This is because we didn't add any other terms in this Hamiltonian. But in principle, you could add some other terms like hopping and so on and so forth. And these properties that the unitary U has translation invariance will be completely lost. But this property is actually quite interesting and important for us to show that this has a quantized bulk invariant. But we will show numerically that if we deviate a bit from this fine-tuned Hamiltonian, we will not lose this quantization actually. Numerically, we will see that. So now we need to define some topological invariants. So we don't have translation invariants, so we can forget about momenta. But what one could do is that we could twist the boundary condition and insert some flux. So then the bulk topological invariant that we want to compute, which is the third winding number, could be just computed in that flux space in principle. So that could be a way. And it turns out that for this to work, we would need the spectrum as a function of phi to have no degeneracies. In particular, we can see that the spectrum without any flux has a typical level spacing of 1 over the volume, okay? And because the matrix elements of our unitary are exponentially decaying, by applying a finite flux here, the energy of the states will actually just change by some exponentially small correction. Therefore, and this correction is way smaller than the level spacing. Therefore, the spectrum would be continuous as a function of the flux. And in principle, we could just compute our invariant using these flux insertions. But this will turn out to be a bit too slow in 3 dimensions and will actually take another route that was initiated by Emil Prodan and collaborator that relies on a non-commutative geometry approach. So there they defined some real space winding number that takes this form. So it takes as an input the unitary matrix U, which is our unitary that decays exponentially fast, okay? And we just compute this object where xj, xi, and so on are just position operators. And as long as the matrix elements of U are exponentially decaying, we are actually ensured that this is integer valued, okay? So because it is the case for our problem, then everything is fine, we can compute it. And in particular, in the case of finite size, one needs to replace those commutators by even number of flux insertions. So we need to replace those commutators by those brackets here, where we have those linear combinations, and then we just have some numerical coefficients that one can evaluate, okay? So then we have a way to get our, at least numerically, we have a way to evaluate our bulk invariant without any ambiguity because the matrix elements are decaying exponentially. So now, the question is, what about the surface? So we know by construction that the surface carries some Hall conductivity, at least if we apply open boundaries in the z direction. So what we should compute on the surface is some Chern number. So then we can compute the Chern number using this real space formula that was also introduced by Emil Prodan, replacing here the commutators once again by those brackets. So then we just need to define some projector on the surface. Let's say we apply open boundary condition in the z direction, we have 2 surfaces. Then we just want to project on, let's say, the left surface. So the way we can define this projector is just by removing states in the bulk. Because all the bulk is fully localized, we can just safely remove some states that belong to the bulk. And if we remove enough of them, we'll be able to completely decouple the two surfaces. And then because the 2 surfaces will be completely decoupled, we can unambiguously define some surface projector on one of those 2. Okay, and then we can just input this to compute the Chern number. So just to summarize, because we have this unitary U that has exponentially decaying matrix elements that ensures, and we can show it analytically, that the winding number of such a unitary is 1, and this will be our non-trivial bulk invariant for our TLI phase. And by construction, the Chern number on the boundary, if we apply open boundary in the z direction, is 1. This is just by this stack construction that we made. But just note that the construction that we made was very anisotropic. So in particular, there is no way, I mean, one in principle might not expect that the Chern number is still quantized by applying open boundary condition in the 2 over directions, let's say x or y. But it turns out that this is the case. If we compute numerically this Chern number in directions x and y, we also get that it is quantized, and it is quantized to the same number. So then we have this non-trivial surface invariant for the TLI in each direction. So we have kind of a clean bulk boundary correspondence here. Okay, so this is very nice, I guess, but one needs then to to verify that this survives perturbation of the Hamiltonian. As I said before, this is a very fine-tuned Hamiltonian. Now we need to go a bit, we need to go a bit beyond such a Hamiltonian. And for instance, what could do is one could just add some nearest neighbor hopping term in that Hamiltonian, which is controlled by this lambda here, which is just hopping strength. So by Anderson localization, we expect that there exists a finite value of hopping strength, lambda c, below which all states are localized. So as a way to verify this, we can just do a level spacing analysis. So we can just look at this Hamiltonian h of lambda, diagonalize it, get the eigenvalues and look at the level spacing. And then we can define this so-called Rn, which is the level spacing ratio. And we can average it over the spectrum and disorder configuration. And then this average level spacing ratio will actually be able to tell us whether the states are localized or not. In particular, it will tell us that we'll go from, in the thermodynamic limit, at lambda c, we'll go from a Poisson ensemble for the eigenvalues to a Gaussian unitary ensemble. So the Poisson ensemble will correspond to eigenstate being exponentially localized, so with compact support. While in the Gaussian unitary ensemble, there will be some states that are delocalized, okay? So then we can just evaluate this critical value of lambda, this lambda c, just by computing this average spacing ratio for different system sizes. Because it turns out that this object has scaling invariance at the phase transition. Therefore, the value r of lambda c is just independent of system size. Therefore, all these curves should intersect at only one point. And this point will tell us the true value of lambda c in the thermodynamic limit. So we can, from there, evaluate that this value should be about 0.088, basically. Okay, so now we know that there exists an extended localized phase for this system when we add nearest neighbor hopping. So what we can check is that whether the topological invariant on the surface and in the bulk will actually still be well quantized for lambda being smaller than this lambda c. So this is what we checked numerically. So first thing is that we computed this NTLI, which is just the surface invariant. So it's just the Chan number of this surface projector, let's say on the left surface, let's say with open boundary condition in the z direction, and then averaging over disorder. And we found that by increasing system size, the plateau where this number is quantized to 1 gets wider and wider and converges towards this critical value lambda c, which should be the value of the transition in the thermodynamic limit. So what you would expect in the thermodynamic limit is that this is quantized to 1 up all the way until lambda c, and this is always 0 after, because you are in a metallic phase and you don't retain any topological properties anymore. So then this is what we saw in the case with open boundary condition in, let's say, the z direction. We also check that this is the case for open boundary condition in 1 direction, let's say the y direction. And we also see that by increasing system size, we really observe this quantized plateau of this surface Chan number. So this is for the surface invariant. Now we can also look at the bulk invariant. So the bulk invariant is given, as I said, by this third winding number, disordered third winding number, that is then averaged over disordered realizations. And one can also show, one can see numerically that by increasing the system size, this plateau where the bulk invariant is approximately quantized to 1 gets wider and wider, okay? So we also expect that in the thermodynamic limit, this will go all the way to lambda c, although it is kind of hard because we are dealing with this ordered system. It is not extremely easy to go to very, very large system sizes, but we see that the behavior is the one that we expect. Okay, so finally, we would like to see some quantized response associated to this phase. As we've said before, this phase has insulating boundaries. There is one delocalized state on the boundary, but the rest are localized states. So basically, these boundaries are insulating. So it's not very clear a priori how to measure a quantized response from the bulk. So because on the surface we have anomalous Hall effect, one might think that we should use some measurements. We should actually get inspired by measurements that are used to measure Hall conductivity. So one is the 4-terminal Hall measurement, where we just apply some longitudinal current and measure transversal potential difference and get quantized Hall conductivity from there. And one could also alternatively deform this rectangle, two-dimensional rectangle, to an annulus and use a so-called Corbino geometry. So then we just apply in the middle of that annulus some time-dependent magnetic flux that goes from, let's say, 0 at time 0 to one quantum flux phi 0 at time capital T. And by Faraday's law, this will induce some tangent electric field that will induce some current flowing from the inner to the outer circle. And by the Laufling pump argument, this charge transfer from the inner to the outer circle would actually be quantized and be given by the quantized Hall conductivity. So that would be another way in principle to measure something quantized out there. So one could first think about this 4-terminal Hall measurement for our system. So first, we should just remind that on the boundaries, as long as we impose open boundaries in one direction, then on each surface, there will be one delocalized state at some energy, let's say, at some energy, at some given energies. And if we just tune the surface Fermi level, when we go through the first of those delocalized states energy, the Hall conductivity will jump to a quantized value of 1, and then when we feel the second delocalized state, it will jump back to 0. Okay, but then if we apply open boundary condition in all the three direction x, y, and z, we might actually, so we just put the 4-terminal in this way, okay, and we might actually expect that some chiral hinge state will appear on for instance, this hinge. If we take our surface Fermi level to be, let's say we take this, we say that the surface Fermi level is below the energy of the delocalized states of the upper phase, but it is larger than the energy of the delocalized state on, let's say, this surface. Then because one will be one, okay, in that case, we'll actually be able to have some chiral hinge state that will flow on that hinge between those two faces. So then if we reapply also this constraint on the 3/over faces, we really have some chiral hinge state that will be able to connect all the 4 Hall bars, and then we can get a non-zero measurement in principle. But there is a serious drawback here, is that actually the energies of those delocalized states are actually Bok independent. They don't depend on the Bok. They don't depend on the Bok topology at all. So in particular, you could just glue some Chan insulator on the surface of the TLI, and that would completely change those Fermi energies. And in particular, you could just glue it in such a way that those two delocalized state energy would be equal, and therefore you would not have any quantized Hall conductivity anymore. So in that sense, this is a very extrinsic signature that cannot distinguish our phase from simply a trivial insulators on which we will glue some Chan insulator on the surface. So we need to go for something else. And as we've seen before, the other alternative for the Hall conductivity is the Corbino geometry. So this is what we will now consider. So we will consider this Corbino geometry in 3 dimensions, and we consider that the Bok is empty and that the surface is fully filled with electrons. And we've read some time-dependent magnetic flux that goes, let's say, from 0 to phi 0 after one period. So in that case, you'll get some charge pumping that is quantized by Laufling pump argument around the cross section of this Corbino disk, this thick Corbino disk. Okay. And now what one can do is that we can apply some gate voltage at those two, at the two sides of these cross sections in such a way that actually the current will, only in the steady state, only the top part of the surface will be filled with electrons, and therefore the Laufling pump will actually only connect the source to the drain, but then the drain will not be connected back to the source because of the chemical difference. So here, chemical potential difference. So then here we'll only have charge transfer from the source to the drain. Okay, and in that way we can get a quantized charge transfer from source to drain. And this really distinguishes our setup to a simple trivial insulator on which we will glue a Chan insulator, because in that case, if we fully fill the surface, because we have only two delocalized, we will fill the two delocalized state of the Chan insulator, and therefore the Hall conductivity will be 0. While in our case, because the surface of the TLI is anomalous and is kind of half a Chan insulator, by completely filling the surface of the TLI, we retain a non-zero Hall conductivity, and therefore we can get a non-zero charge pumping in that setup. So in that sense, it's really an intrinsic signature from the Borg topology. Okay, so now it's time to conclude. So we've been discussing families of non-trivial insulators that are disordered such that all the Borg states are fully localized. And instead of the usual expectation to have only trivial Anderson insulator, one can have actually infinitely many non-trivial TLIs which have insulating boundary that are anomalous and that have delocalized states, one delocalized state per boundary. Okay. So in particular, there are different things to explore now. One could consider, so here we've been considering a setup that was in class A. So there was no particle symmetries, but we could now consider the same construction with time reversal symmetries or over symmetries. That could be a way. One could also consider the role of interactions and maybe look for the link with many body localization. And what could also think about a generic classification of such a phase. So here we've been dealing with only one particular construction with these stacks of Chan insulators, but there might be different ways to construct these non-trivial insulators with fully localized Borg. And it will be interesting to understand the complete classification of such. So with this, I would like to thank you for your attention. I would be glad to answer any questions if there are any. Yes, Anton?
Yeah, thank you very much. Really nice talk, and I really enjoyed thinking about these concepts. I have a couple of questions.
Mm-hmm.
First of all, now thinking about the bulk delocalization as a necessary complement of topology, it's true in some symmetry classes, like in Chern insulators. But
Yes.
for example, if I take the Kitaev chain, it's very easy to have the Kitaev chain fully delocalized because the particle hole symmetry only acts at zero energy. So it's very easy to have Kitaev chain fully localized and still topological. Is there, which is of course not anyhow contradicting your work, but is there an analog between this construction and phases where topology is not accompanied by delocalization?
That I don't really know, to be honest. So would you think of constructing such a phase starting from, for instance, Kitaev chains, like a two-dimensional systems made of Kitaev chains, or?
Yeah, well, yeah. That's so. For example, if I take a three-dimensional system, which is just a stack of Kitaev chains, I can very much write an invariant for it. It's probably it's likely one of the weak topological insulators. It's also fully localized in the bulk, but it has actually a metallic surface.
I see. So then the surface kind of signature would be different in that case.
Yeah, right.
Yes.
I guess it's a relatively vague question because I don't actually know what my question is, but I was wondering.
Yeah, but I think at some point we're also thinking of maybe constructing like a two-dimensional system made of Kitaev chains. But it was not clear whether by doing that kind of stacking with coupling the layers, whether this would be, we would not mess around with the particle hole symmetry. It wasn't so clear to us when we're thinking about it. So, but yeah, this is interesting.
All right. Another question I actually have about it's more about this model. So how do the side surfaces look? You attribute a Chern number of ±1 to top and bottom surfaces, but
yes.
What's the Chern number of the side surfaces, and is it well defined?
What's the Chern number of the side surfaces?
Yes.
What do you exactly mean?
Well, the side surfaces, I mean the surfaces that are perpendicular to the stacking direction.
Okay, I see. So can you repeat the question again? So on these side surfaces, what?
Yeah, is there a way to define a Chern number? And if yes, what is the Chern number?
So analytically, we could not show that it has quantized Hall conductivity on those like those transversal surfaces, like let's say X and Y. But that's what we observed. So I think it's written here. It is a numerical observation that actually, although this is very anisotropic, in the end, we get also quantized Chern number to, like it also the same. You get on one, if you apply, let's say, open BC in the X direction, you also get that one surface will be -1 and the other will be +1. So it's exactly the same as for the Z direction, which was also maybe kind of surprising. Because yeah, this is very like anisotropic construction, but still, and I think there's also a plot here of this open, like here it's a surface invariant as a function in the Y direction, and it's really quantized to 1. Which is, I guess, also maybe in contrast with this construction of weak topological insulators, right? By stacking this, where I think maybe we wouldn't have on the perpendicular surface to the stacking direction, we wouldn't have something quantized, I guess. Well, here it seems to be the case. Yes.
I want to ask about this bulk boundary correspondence in your system.
Sure. Yes.
So if for instance, maybe slide number 9, I think is
slide number 9.
slide, because you have a big picture there. So the bulk is fully localized and it's filled with states which are trivial. And
yes.
And on the surfaces you have these states which are delocalized and they carry different Chern numbers, like
opposite
+1,
ones. Yep.
opposite ones, like +1 and -1. So I can understand like these states cannot be localized by disorder because they carry opposite Chern numbers. So the only way to make these states disappear or become localized is to have them annihilate with each other.
But
so
then
they must be exactly.
Yeah, exactly.
So you must bring them both at the same energy and at the same real space position in order
and the problem
to have...
is about the real space position, right? Because the bulk
Yes.
is fully localized. Yes,
So
exactly.
that's exactly my problem about the real space position. Why can I not take these two opposite Chern number states and make them overlap in real space by dragging them along the surface instead of dragging them through the bulk? Is there some symmetry that's stopping me from doing that?
Well, here on that picture, so okay, here on that picture, there are only, let's say we only have open BC in the Z direction. So we would have periodic ones. But I think what you mean is that if you would consider, for instance, a sphere, like something that has a connected surface, right?
Mm-hmm.
So I think in that case, in the case where we would have a connected surface, there would actually be only one delocalized state.
What do you mean by connected surface?
I mean, like a surface where you could, in principle, just bring the two delocalized states without any trouble, right?
Mm-hmm.
Like a sphere, for instance, would do the job, I guess. Like it's a ball which has a spherical surface.
So, what would be an example of a state which of a geometry where I could not do this?
No, actually, yeah, no. That was, I guess, actually, most would do the job. You're right, yeah.
So then it's possible then to trivialize this system and remove the boundary signatures without touching anything in the bulk.
So to my understanding, if you would have, for instance, like that kind of surface, like a sphere, you would only have one delocalized state. So you cannot annihilate it because there's just one, I think. But I might be, yeah, I might also need to think a bit more about it. But that's
I think somehow the total Chern number of all states in a finite system has to sum to 0.
Mm-hmm. Yeah. Yeah, I would need to think a bit more about it. Yeah, yeah. But that's a good question indeed. Yeah. Mm-hmm. Sorry.
Thank you.
Yes, Anton.
Yeah, so perhaps actually, I mean, Cosmo raises an interesting point. So also thinking about what happens in a finite geometry. Indeed, it seems that that there's nothing in principle that prevents the two layers with the opposite Chern numbers to couple at the sides. But at the same time, it seems that if I take a macroscopic sample, then, for example, the bulk polarization and the response to magnetic field would still stay finite and quantized. So that, I think, seems to keep the phase non-trivial, right?
Non-trivial. But even, I mean, in some sense, the surface of the surface of this system, apart from those two delocalized states, all the other states are fully localized. So I don't know if it's so clear that you could bring them on by just you know, by just traveling on the surface of the system, because everything is fully localized on the surface also, apart from those states. But yeah. But
actually,
yeah, you're right.
Sorry, as a follow-up, if all states are trivial and fully localized in the bulk, would it be possible for me to remove them, let's say one by one, until without destroying any of the topological signatures of the system, and I just take one of these fully localized trivial states, I take it out, and I do the same to the next one, and I do the same to the next one, until this three-dimensional system ends up being a two-dimensional quantum Hall effect? Just to reverse the direction of the question, if I take a two-dimensional quantum Hall bar and fill it with trivially localized states to make it thick in 3D, would I get a topologically localized insulator?
That's also a good question. Can you repeat, please, what your construction?
I'm wondering about the relation between this and what's called extrinsic topological insulators.
Yeah.
Basically.
Yeah, so it's something that we've actually been thinking of, this relation between extrinsic topological insulator and such. But I think this is also something that I was explaining towards the end with this Corbino setup, that I really think that on the boundary, you would just have one delocalized state with the TLI because it has anomalous boundary, while the extrinsic system would be trivial. Okay, you just glue some channel insulator right on the surface of a trivial insulator. In that case, you would get two delocalized states on the surface because it's channel insulator. So then if you fully fill the surface with electrons here, you would get something zero Hall conductivity in the case of extrinsic topological insulator, where here, because there's only one delocalized state, when you fully fill the surface, you get non-zero Hall conductivity. So to me, that's kind of the way to distinguish them even physically at the level of this setup. But I agree, for instance, if you consider that kind of Hall bar measurements, here you would not be able to distinguish this phase from an extrinsic TI. This would really just be the same, because you can always glue something to make, for instance, this chiral hinge state, you can make it disappear by gluing something else on the boundary. But I think, yeah, on this genus one geometry, one can really distinguish them, this extrinsic and the TLI.
So if I take a 2D quantum Hall system, which is this red rectangle in your picture, and on top of it, I just add trivial states. I just add like atoms which don't do anything on top of, and on the bottom, and I make a big column out of this initially 2D churn insulator, and then I glue this column somewhere far away in order to make a Corbino with completely trivial atoms everywhere, except for this initial 2D Hall bar, which is shown as a red rectangle. Have I gotten a topologically localized insulator?
Yeah, so then this I would need to think a bit more. It might be that I would need to think a bit more, I think. Yeah, that's a good question. Yeah, okay. Is there any other questions, by the way? Or...
All right. Doesn't look like there are further questions. So thank you very much once again, and have a nice day.
Have a nice day too.
Everyone.
Thanks. Bye.